Let's talk about what do we expect from this situation in terms of technology development, and what science opportunities do you think are realistic within the next time frame? So maybe, Mahmouda, starting with you in terms of technology, what do you think is possible, and when do you think we will be able to benefit from the new technology that you and your colleagues are developing?
Yeah, of course, I'm very hopeful that we will have matured the technology within the next 10 years or so, and hopefully we can do some exciting mission within the next 10 to 12 years or so.
With the technology that you develop in your lab, and I guess looking at what is being developed elsewhere, so I think with quantum dot spectrometers, they're amazing. Mm-hmm. So, but I'm sure you have other technologies in the laboratory that can be flown soon.
Yeah, I'm also developing another technology, another instrument for in situ chemical analysis, which is also highly miniaturized, low power, small, light. So that's actually another possibility to fly with some of these solar cell missions, to not only do spectroscopy, but also do in situ chemical analysis. Mm-hmm. So currently the TRL is, of that technology is about 4 or so. And my goal is to develop, bring up the TRL to 6 or higher within the next 2 to 3 years. But of course, it's not just my instruments that are needed, right? We also need several other technologies to have a solar cell mission, kind of like ScienceCraft or other solar cell missions. I think finding a solution for small, low power, small and light power solution like an RTG, would be needed. Also finding a solution to send data, as much data as we can, at a relatively small, low power comm system. I think that would also be required. For our mission, we're looking at several possibilities. There is quantum comm initiative at NASA Goddard. Optical comm is also something we're looking at, but from our initial investigation, it looks like it might be too large, and heavy. So yeah, there are other technologies that need to be developed as well, but I think the technologies are being matured at a relatively faster speed than it used to be in the past. One challenge for planetary science, though, is that a lot of the bigger missions in planetary science are often prioritized by the Decadal Committee. And the Decadal Committee picks or selects missions that use higher TRL technologies, So from that perspective, I think one advantage the solar cell missions have is that it's so much lower cost, we can potentially fit within the cost cap of SMECS missions. And I think planetary science community is a lot more willing to take risks for SMECS missions. So I don't see solar cell missions being selected for, larger missions like Discovery or New Frontiers over the next 1 decade. But I think as a SMECS missions, it's certainly, some solar cell mission is certainly possible within the next 10 years.
In our work on the solar gravitational lens, we realized that we need to deliver a meter-class telescope to those distances. And with solar sailing, essentially, where you're limited with mass, what we realize is that we can do in-flight aggregation. Once you fly several of those small sats, once you go around the sun, once you move in very fast, now you have several Lego blocks, essentially, and you built your spacecraft out of a Lego block that is moving already very fast. So there are some ways actually to make mission-capable spacecraft and to deliver more instrumentation to the destination you want within the solar system. And I guess in this case, maybe this heliophysics would be the easiest, in a sense, to realize. So Sarah, looking at your presentation, it's clear that maybe one of the first missions, we can go around the sun, the polar region, and that would be the holy grail of heliophysics. And so, if you can talk about what type of instruments do you think we should have on those missions?
Yeah, thank you. I find the idea of using these, having the capability of sending up lots of small, cheap missions really compelling, because there's an urgent and immediate need to go and see what's there, first of all. But there's also a need to get a more sustained view and a more comprehensive 4-pi type coverage. And so the idea of a more disaggregated approach where there's a standardization and understanding of what the key instrumentations are, a miniaturization of them, and then they can go up whenever there's a ride share to fill a slot. And it can be different agencies, different countries, different groups like this one who could be sending things up. And you'd need the magnetic field pretty much everywhere, because that's the boundary condition of the magnetic field of the photosphere pretty much everywhere. But you could also, what could you learn by sending an irradiance, spectral solar irradiance measurements up to the poles to look down and to understand how things change from pole to equator? What can you learn that would actually transfer beautifully to stellar physics? What could you learn by observing the corona at different wavelengths of light? And for that matter, I've been focusing on imagers, because that's the thing because Ulysses sent up in situ samplers, so they measured the solar wind locally as opposed to taking the images. But solar wind, there's a need for monitoring the solar wind throughout the solar system, to have buoys between the sun and the earth to see what's coming in terms of a storm, to build, to get a sense of the structures of what's coming throughout the solar system, honestly. So I would say magnetic field's number one, both in terms of magnetographs and the magnetometers. The helioseismic measurements can pretty much get be the same instrument, because they're just looking at the Doppler shift of the intensity, the visible light, usually intensity. And then going into the EUV for imagers, doing spectral polarimetry, being able to look from above and get the magnetic fields in the atmosphere of the sun would be phenomenal. Honestly, there's almost no limit. Once we go to the poles, we're going to need to take measurements, a range of measurements, to try to build our understanding of the entire system.
And we can form trajectories, those that will allow you to monitor a certain pole for a longer time.
Yeah, being able to be up there for a while is really important, because for the helioseismology, you need to get the noise levels down. And so a lot of helioseismology is done from the ground, and there's very important scientific results that are the product of basically decades of measurements, where the noise has been reduced to very, very low levels. And so the longer we can go and sit and integrate, the better, frankly. So having something sitting up there would be wonderful.
Excellent. Maybe going to our online colleagues. Ben, you're there. I see your face. So going into an asteroid and trying to understand the surface of the surface composition. So with the instruments that you have in mind, do you think it's achievable within the next, what I would say, 2 to 3 years? So can we get there and study the surface and understanding what is happening? What is the history of formation of that object? Can you deploy systems like this from a sailcraft?
So I think Ben is not online.
Ben is not there. Oh, I'm sorry. So, good. I see. Very good. So, unfortunately. So then, Penny, I see you here. Wonderful. So then...
I am here.
Wonderful. This is good. We heard from Francis that going through plumes of Enceladus, for example, with fast-moving sailcraft, we probably will, the molecules will break. And so, if we take any data, do you think there is other ways to actually get into to study biology on the fast flyby missions?
Well, my suggestion about mapping Tholen is the one that I can think of. I think that an active capability to fling stuff down and actually, hit the planet or the moon could be interesting. If those were coming down at a velocity that was significantly less than the actual solar sail master craft as it goes by. And one of the things I didn't mention, of course, are all the NIAC studies that have been funded to look at distributed tiny items. I had 4 or 5 of them listed on the slide that I had to skip because I was running out of time. But some of them are appropriate for bodies with atmospheres. Some of them are appropriate for bodies with no atmospheres. Some for both. There are fluid floaters and swimmers and all this kind of stuff. I mean, one of the ideas that I thought would be cool is some sort of a percussion shooting of very limited capability sensors, actually into the tiger stripes. So I think there are a lot of things that you can do, but I don't see those as very near term, because I think the flybys make the most sense for the early phases of what you can see, and we have a very large amount of solar system to interrogate. So I would be happy with mapping Tholen where it occurs on objects related to Pluto and Charon, out in the outer solar system. And how much tasty goo is out there so that early life can have a free lunch, I guess is the bottom question.
Very good. And I remember you asked the question about how precisely those systems can be navigated. So ultimately we have a veined approach where initially after going through solar perihelion you are able to compensate for any trajectory injection errors. And then you have onboard electric propulsion that will allow you to nudge the trajectory just ever so slightly, so you can get to your destination with reasonable precision. And that's something that I think it's very, very exciting. You can go through those plumes eventually. And,
eventually.
Konstantin.
I'm sold, I want one.
Excellent, very good. Konstantin, look, the parameter space, the volume of exploration that you brought into the discussion, I mean, it's humbling. So how do we go about deploying the systems that will bring us the most benefit into helping you to identify, locate Planet 9 or find other objects, because it's a significant volume out there. What do we do?
Yeah, it's a great question. I think there's really 2 approaches to take, but both of the approaches will require the spacecraft to be able to, I think, talk to one another, right? The first approach, which I think is the don't need to move, super fast, although it would help approach, is you put spacecraft in orbit of the planets, and if there's clocks on the spacecraft and they're able to talk, with one another, then they it can get precise distances between them. You effectively measure the tidal field, the tidal deformation of the orbits that is instilled upon them by Planet 9. And for the Earth, it's about 1 meter. And so, if Planet 9 is there versus not there, the difference over a single orbital cycle is about 1 meter. So that's the order of magnitude. The other is to say, okay, we don't know where this object is in its orbit, right? We don't know the phase, but at least we sort of know the plane, because the plane is the plane of the distant KBOs, right? The reason distant KBOs are tilted by about 20 degrees is that's the Laplace plane out there. So the other kind of way to go is to say we're just going to uniformly send radial objects along that plane, right? And you try to measure their deviation, right? And kind of compute the acceleration that way. That's the more, I think, brute force approach, but it's kind of awesome.
I guess the more we send those inexpensive sailcraft or spacecraft in the deeper solar system, and the precision tracking will allow to get useful data for your research, definitely. And excellent, thank you. Francis, do you see a way of doing air braking when we go through Titan's atmosphere? With this velocity that we are talking about, are we totally burning through, or there is a way to actually to do something useful?
So it's a good question. I've got to imagine it's tricky because you need to go deep enough in the atmosphere to slow yourself down, but not so deep that you burn up. And at those kind of velocities, 30 kilometers a second, I think that's going to be hard. Maybe you can do something clever by getting yourself captured by Saturn, for instance, and losing your velocity that way, and then circling back to Titan. But I would have thought that a straight shot to Titan would probably end you up in trouble. I haven't done any calculations, but that would be my guess. 30 kilometers a second is really fast.
The speed is advantage, and speed is disadvantage as well. So we need to think about the mission architecture such that will be uniquely qualifying different objectives, scientific objectives. And in this case, I guess this may not be the case, or maybe not among the first ones. At some point, we'll come up with the shielding and we'll be able to do this. But at least we are talking about this, and at some point we may fly. Maybe at this moment, I'd like to open the floor for discussions, maybe from the audience, so that I will not monopolize the discussion here. Ron, please. Marshall, you're here.
So there was one thing that really struck me with your presentation, and that was how the not magnetospheric, but the magnetic instrument, it's not a magnetometer, but the camera, gained by 3 orders of magnitude or 4 orders of magnitude in terms of reduction of mass. How did you do that? What happened there? I mean, because generally it's like a factor of 10 is a big deal. So how did you get, a factor of 1,000 out of it?
So first of all, it's not me,
Okay.
but that was my last slide. I was showing the micro, which is a technology in development. It's pretty low TRL, but it's in development right now. It's Neil Hurlburt at Lockheed is the one who's working on it, and it's using photonics. And frankly, that's as much as I know about it.
So it's photonics.
It is photonics. Yeah.
Ron, you were... maybe Harry, if you...
Oh, okay, yeah. Konstantin touched on the subject of timing, and so I wanted to note that there is a coming generation of very compact, extremely high precision timing and frequency measurement tools, chip-based tools, atomic clocks, and frequency comb instruments that I think could really revolutionize timing and metrology. And I'm wondering whether some of the other panelists and speakers could actually comment on what would be the implications of, very compact arrays of high precision, frequency, and timing measurements.
Absolutely. With the timing on board, I think we are able to improve the orbit determination. And so this way we can study the distribution of dark matter within the solar system, inverse square law, gravitational inverse square law. So there is a lot of applications for clocks on board. And so if we're able to synchronize and transfer the time between different devices, so I think that will be a unique contribution to multiple areas. And we will be able to identify those planets that are lurking out there and not being detected. So with these clocks, I think will be very interesting contribution. Konstantin, would you add something to this?
Yeah, I think it's a really important point, and I guess I am not an expert in this, but I do have I think more questions than I have answers, and my question actually concerns drift. So like with atomic clocks, my understanding is that sort of the more you pay, the less they drift. And that's going to be important on a time if you're trying to measure, right, the tidal deformation of an orbit, right? You need it to not drift on time scales on the order of years, decades. Is that something where the progress is being made at a rapid pace at the moment?
I don't think those systems will be as compact as we want them to be compact anytime soon. So maybe we are not talking about those systems just yet. Mm-hmm. But then doing differential measurements between pair of spacecraft. Then you have a network of clocks flying next to each other. And this may be a way to tease out some science that we're interested in. But doing absolute synchronization between the clocks on the ground and in space on the matter of years, I don't think the size matters in this case. So there will be very large clocks. So, other questions?
Yeah. Okay. Yeah. For those of you who don't know me, I'm Ron Turner, and I'm the Senior Science Advisor to NIAC. And NIAC is really pleased to have the opportunity to, forward fund things that get picked up here at Breakthrough Discuss. There's a lot of fellows that are standing around. This is not going to turn out to be a question, but you're allowed to comment later. It's that in particular for this session, we funded several advanced solar sail concepts. NIAC's got a phase 1 and a phase 2, but we also have this thing called phase 3, which is real money, $2 million for a couple of years. Phase 1 and phase 2 are not insignificant. Slava has got one of our phase 3s and has used that to develop the solar sail concept. He talked about that. We have a couple of phase 2s that are solar sails. I'm going to limit myself to solar sails, and I'll probably miss some, okay? But Arthur Devoyan has had a phase 2 on the concept that Slava's picked up for his phase 3. One thing the reason for standing up is one thing that was recent, and probably too recent to have really led to an invitation here, was Grover Schwartzlander's diffractive solar sail, unless they're represented here somewhere. Oh, good. Oh, well, there we go. Great. His concept was picked up for also a phase 3. It's being led by Amber DeVille at Johns Hopkins. The significance of that is they changed the PI so that they could really put a mission-oriented space weather group, in the forefront of the mission planning, taking advantage of this diffractive solar sail. So, it's really great that so many people are interested in these solar sails, and NIAC is really happy, to have the opportunity to, to support these advanced solar sails. And again, I left out a whole bunch of fellows that are in the audience, but only because I'm limiting myself to solar sails.
Ron, thank you, and thank you, NIAC, for the work that you were able to support. It was a very exciting opportunity for us to work on this. Other questions?
Shall we go to Grover Schwartzlander is on Zoom.
Absolutely, yes. So, could we talk about diffractive sails? What do they do? We haven't discussed them in the session, but could you comment on what are those new type of sails are going to be helping us with?
The main idea is that, unlike a reflective sail where you have to tilt the sail with respect to the sun in order to get a transverse force so you can either decrease your orbit or increase your orbit. Here we can, with diffractive sails, the light gets deflected by a diffraction grating or maybe even a metamaterial type of subwavelength diffractive structure that deviates the light more than effectively you could get with a reflective sail because it can be sun-facing. This gives rise to a simpler attitude control scheme so that the sail is not at some kind of odd pitch and you have to keep kind of try to manage around that. But we also believe that with advanced materials, we can get very high efficiencies and presumably lower masses so we can get accelerations. Giving rise to our thanks to Ron for mentioning our recent award. The work actually starts in October. The idea is to put a constellation of solar sails around the sun as high as 90 degrees inclination angles. And the idea is that, it's very exciting to hear these talks. Everyone seems to be converging on the idea of cheap, low mass, maybe 1 or 2 instruments per spacecraft. But you put a bunch of them up there, each of them can be doing their own things and to get the mass problem resolved. And so that was my idea, is to put this constellation up there. Amber DeVille, who's the PI, she was my student at RIT who did her thesis on basically an orbit that we basically showed by just taking the sail and just, as you go around the sun, you just basically rotate it back and forth like this, and you increase your inclination angle and you drop your orbit. So we can get down to like 0.3, 0.5, for example, and up to 60 degrees inclination or higher within 10 to 12 years.
Excellent, thank you. Maybe I want to make a comment here by recognizing the fact that there are many solar sailing mission ideas and the projects around. But reality that we face is not as bright as we would like it to be, because the funding is the issue. Programmatic issues here are very significant, because graduating from NIAC Phase 3 program, it's a wonderful event, but then you're off the kindergarten, you go to high school immediately, so you have to move rather fast. So it's a challenge for our community, because we definitely offer something unique. But now we need to find a transition and establish this technology into the mainframe of agencies or philanthropic organizations that will be interested to consider those missions. So it is something that solar sailing need to embrace, and maybe with the help of NIAC and NASA and other organizations, we need to recognize that this is the new area which is not yet fully supported within established players in this field. So do you have any comments on programmatic issues? How do we go about flying missions? So yes, we're ready to fly, but then there is a next step. How do we go about it?
Yeah, I can add that that was definitely my concern as well, which is why I was trying to look for opportunities within the existing programs, and I talked about the programs in planetary, where this type of solar cell might fit, which is, I think, SMEX, if we want to do something over the next 10 years. But yeah, funding is definitely one of the big concerns.
Sarah, would you?
Yeah, the question is, how does it fit into the existing paradigm, or does that paradigm need to be completely disrupted to make it happen? I don't know. I mean, it's such an interesting idea. You were saying about 20 million, right? And the 1 million, the CubeSats at a few. How much are NASA CubeSats now?
They're 25. They're 5, 10 different.
Yeah, 5, 10. So I mean, there's some space there, and then possibly you could do something. Could you have a SMEX proposal where you had 10 of them, or wait, how does it, maybe not quite that many would fit, but up to the budget, and then and what could you do with that kind of a configuration, and could you get it to the point where it would be not risky, and so you wouldn't be up against all the issues there? I don't know, but I think we have to come up with new mechanisms, perhaps.
Absolutely. I think it's a reality is that for the last 30 years we heard Lou Friedman name. There were other people who actually contributed to the development of solar sails. So there are many people in the community, but the point is now we have all the key ingredients for the solar sails to be successful. There we have low mass spacecraft, miniaturized electronics, we have materials. Now it's time to start flying. And as you test as you fly and fly more often so that you improve your technology, that's what we need. And realistically, this is the program we would like to establish within NASA, within organizations, within the community. So our wonderful panel, yes.
Just one question. If you want to fly, one of the things you need is power. And so this question is for Mahmouda. You had mentioned that thermal management and power were key challenges for you, and depending upon what you choose for your thermal management solution, that's going to give you parasitic power and tax as well. So can you talk a little bit about what are the solutions that are on the table, and just a few minutes about that.
I can talk a little bit about it. We looked at different options, and it seems like solar cells might not be as efficient in outer planets simply because we're just so far away from the sun. And our best bet is probably a small RTG. But then when I was looking at RTGs that are available within Planetary Science, technology development program, it seems like they're not currently working on a small RTG development, and R&D is expensive. So talking to the program manager for that program, she said that they could potentially invest in the development of a small RTG if there are potential missions. But currently, they don't have much work going on in that area. So that is something, that is something we have to look at and we have to fund. Yeah.
There is another NIAC which is funded by NASA. They're developing the program called Apple. Essentially, it's a planar array of small RHU units where you can actually deploy on the sail, and that will enable you to last much longer in space. So that's something that we need to keep and to make sure that this program will actually mature and realize in something that we can fly soon. Any other questions? So maybe James, yeah.
I think, Alexei, are you?
Yes, I'm here. In addition to the question that was posed recently about energy, is there a technology enabling sending information from the solar sail craft back to Earth, like energy source, antenna, and so on? If you are far away, that's a big problem.
What we have with solar sails is a unique reconfigurable system where you can actually, within microwave, if you use microwaves, you can actually change the surface of your sail and essentially use that sail for communication purposes. First of all, you have a very large sail already. So now you need to be able to change the shape of that sail. And essentially the tolerances there are not optical quality, you actually have centimeters quality, and that can be done in flight. Pete?
Yeah, maybe I can add a little bit on that. Of course, we just had our Breakthrough Starshot advisory meeting, and one of the key challenges there is how do you communicate back from Alpha Centauri. And there are a number of approaches being developed to use the sail to reconfigure it as a optical system, and Harry Atwater chairs the group on that, but there looks to be quite promising that we can actually reform the surface or embed elements that could be phased in such a way to optically communicate even across 4.3 light years. So I think it's that this is one of the real exciting things that we came out of our Starshot effort was that the solar sails in our solar system and Sundivers is an early application of the technology that will eventually take us to the stars.
Absolutely. With the technology that we have already, we can go all the way to probably 3 astronomical units. Going further, we can use the sail to change the shape of the sail to communicate. And then once the power source is available, so those that I mentioned, the apples, I think we can go all the way to 40 AU in a reasonable time without changing that much. And so then the next step is we will be waiting for the technology development that is being ongoing in Mahmoud's lab and the laboratories across the country. So technology is here, it's mature, it's capable, so it's time to embrace it. And
I think maybe Penny has a question.
Yeah, it's not really a question. It was really in response to a couple of earlier comments about, how do we make this go forward? The point was made that NIAC is fabulous, and as a fellow, I agree wholeheartedly. But what do you do after the phase 3? And I think that with all new ideas or newly emerging ideas, and solar sail is not new, but its current manifestation, its promise has taken a jump, and the NIAC funding has helped that tremendously. So one of the strategies, the only one that I know that works, is to really essentially get groups of folks interested in writing concept papers and publishing those in the literature, because NASA is not this nebulous thing that makes, omnipotent decisions. It responds slowly sometimes, but responds to demands from the community. So, this meeting is obviously a step forward, and I think that those of us who are scientifically interested in this prospect could potentially team up and publish things in our various journals where we've got, a group of people who can articulate just how this can serve their particular science. So it's just like a political campaign. You have to build momentum. And so, rather than just sitting around waiting for NASA to have an epiphany that solar sails are the way to go, we push from essentially the grassroots. And I say that even though I now work for NASA, but I spent most of my career in academia. So, I've worked both sides of this fence, and I think you can't underestimate the power of a very interested group of potential users.
Penny, thank you very much for this comment. This is exactly what we are doing here. This coming Friday, we'll have another meeting. We will be discussing the Sundiver concept, the plans, how to mature and how to actually start flying. So anybody from this audience who is interested to participate in this meeting, please talk to me, and then I guess we'll see each other on Friday. We'll talk about Sundiver, next steps, how to implement the program. And maybe on this, this time I think I would like to thank our speakers through the session, and thank you for the audience for the wonderful questions and Breakthrough for organizing us for organizing this conference and having the session devoted to this interesting technology. Thank you very much.